All right, good evening. Sorry, it's a good evening. Good day. Good afternoon from wherever we are. So today we'll be continuing from where we stopped, hopefully in the time series. And yeah, Amori, can you make me a host so I can share my screen? Delay. I think I can share my screen. So, so hopefully my screen is visible now. So today we'll just continue from where we stopped when we were talking about the autoregressive process and autoregressive models, and we'll build on top of that. I'll most likely skip to the next part where is autoregressive moving average process. Okay, sorry. I talked about the moving average process and um, the random walk. Most likely I'm going to skip the autoregressive process and move into the AMA process, that is autoregressive moving average process. So today our problem statement is predicting a bandwidth usage of a large data center. Right. So I don't think I'll be able to cover the Prophet side because Prophet is just an automated version of it, right? Of all of this. So if you understand what's going on around here, I think Prophet is just like sklearn dot fit dot predict, right? So you can always look at the documentation for that. Right? So um to brush up to refresh our memory, right? So this autoregressive moving average process is a combination, like this AMA process, the combination of the autoregressive and the moving average process. So if we are talking about a formula, right? If we go to the moving average formula, right? We saw that is the formula for a moving average process is the current value is equals to the mean, like the mean plus the current error term plus the past error term, right? And we talk about how to find this Q, right? How far back are we looking at to determine the current value? So that's when we looked at the autocorrelation function and the auto augmented Kipfler test, right, for the test for stationarity, right? And now the autoregressive function is the autoregressive process has a different function. Yeah, like so to get the current value, it is summation of a constant, right? And previous sorry, the present value is a combination of a constant and past y values and an error term and the present error term, right? So this is the formula here, right? A constant, previous values, right? The previous values, previous series values, and error term, right? So now, if we're talking about the autoregressive moving average function, is the combination of the both of them, right? So it's going to have the autoregressive process and also have the moving average process all joined together. So that's why we have this long formula here. I think I can remove this zoom from here. Right? So yeah, that's the autoregressive process. And remember, in for that, we're going to have to find the P and the Q values, right? The P and the Q values, right? Um, so that's what we're going to be doing today, right? And along the way, I'll also talk about the autoregressive process. So we have a recap, right? So the first thing we're going to do is we are going to simulate an autoregressive moving average process, an AMA process. So I'll be saying AMA from now on, so I don't need to say that whole long thing. Right, so we're going to simulate an AMA process and we're going to build up from there one step by step to how we can actually build a model right, to predict that process, right? So what this is doing here is that we are creating our own process, right? It's possible for you to simulate a process. And so that's what we're doing. We're simulating a process. We're giving it an AR autoregressive process and MA process, right? And we're going to now simulate the AMA process with 1,000 samples of an AMA process. So we're going to have a time series, something like a time series function, right? And if we like do the test for stationarity, right? The null hypothesis of the AD Fuller test is that a series is not stationary, right? That's the null hypothesis. So if we have a p-value less than 0.5, right? That means we're going to reject the null hypothesis and we're going to say that series is stationary. So since we are already simulating an AMA process, right? We're going to always have a stationary value, and that's why we have this low p value. So now we're going to run the ACF test, like the autocorrelation function, and to test for autocorrelation. And the thing we notice here is that we see an autocorrelation, we see the sinusoidal pattern here, right? And remember, we're doing a combination of autoregressive and moving average. So if this was just a moving average process, it's to stop abruptly at a particular lag value, right? Then we see the Q is that particular value, right? But now, since the combination of both of them, we see a sinusoidal process for the ACF test, and also we see a sinusoidal pattern also for the PACF test. Now I'm going to do a recap, right? In the autoregressive process, if we plot, because if you look at the formula depends on past values, right? The formula for an autoregressive process depends on past values, right? And so if you plot the ACF, right, you will get something like sloping down. Why? Because the autocorrelation function looks at the correlation of um, lagged processes, right? What's the correlation between a value at this time and a value at a previous time? And if a process depends on the previous time, it will always have this lag, this autocorrelation plot, right? So now we now see that we can't use these plots to find the P for the autoregressive function, right? And so we have to use another plot, right? That's the partial autocorrelation function. I know I've been saying a lot of things here, and I hope like maybe you can go back with the YouTube video and recap, right? So um when we now plot the PACF, we now see that it stops at a particular value, right? Then we use that value as our P and build up a model, our model with that particular P, right? So so if we now go back to our AMA function, we now see that also it doesn't stop, right? Remember, an AMA is a combination of AR and MA. You see that it doesn't also stop at a particular place. So we have a problem, right? We can't find the P and we can't find the Q because of all these sinusoidal patterns we have. It doesn't stop abruptly, but it has to stop abruptly before we can now choose a P or Q, right? So in the case of this process, right, we now have to do something. We now have to do something called a model. We're going to do some iterative processes, right? And in something like tabular data or classification tasks, right? If you want to get your best model, you use something called maybe the accuracy, or use something called the F1 score, or the precision, or the recall, right? But for time series, it's different. There's now something they call, I don't know why this sounds like an Igbo name, aka information criterion, the AIC, right? And it's a measure of the quality of a model in relationship to other models, right? So it is used for model selection. And the whole formula for this is kind of complicated, and I don't want to bore us with that. But if you go and search for that, Um, why is this lag? Yeah, the AKK information criterion. Go on to Wikipedia or just go here. You see something like this, and this means something, right? The K is are the parameters, and our K is the P and Q, and this is maximum likelihood, right? And maximum likelihood is a kind of whole machine learning topic on its own, right? And I will not want to go into that, but just know we have a metric, right? And we can use that metric to grade our function, right? So now that we have a metric, what are we using that metric for? We're using it for model selection. So what we're going to do is that since we don't know since we don't know what P and Q value we are using, right? So we're going to iterate through a whole lot of P and Qs, right? So here we are creating a range of P's, we're creating a range of Qs, and we're now going to do, if you know Python, right? This is going to create a list, and this is going to create how was it called? An interaction. Like, so it's going to give us a unique values, like almost like a set of these two combined together, 0, 0, 0, 1, 0, 2, 0, 3. I don't want to print this out because it's going to take some time to run, right? So since we have this, we are going to now create a function, right? It's called optimize AMA, right? And that's going to take a list, and it's going to take a list and also a list of a pandas data frame, right? And so we're going to append our AIC, right? We're going to append the AIC to this list, and we're going to build the data frame. Let me go again. This is a list, right? So we're going to iterate through this list, right? We're going to iterate through this list, build it what do you call it, an AMA model. Remember, we're using the Sarimax things, right? Because the Sarimax is the overall, right? We can use the Sarimax to build an AR model, MA model, AMA model, IMA model, blah blah blah, right? So what we're going to do, we're going to now input those values, right? Remember the order. If you remember, the order is where we can change the P, D, and Q. All right, so this starts from P, this starts for D, this starts for Q. And we're changing the P's and the Q's. This and this. I hope you can see my mouse. P and Q. So well, remember we're changing the P's, we're leaving the D because we have not gone to that, and we're changing the Q's, right? And we're going to build the model, feed the model, right? And we're going to calculate the AIC and append it to the list. Then we're going to use that list to create a pandas data frame by naming the columns PQ and AIC. Then we're going to sort in ascending order, right? And after that, we're going to return the data frame. And we're printing out the data frame. And we see a whole lot of values, right? And now we see that, oh, please. I hope I'm audible because I just got a notification that my internet is unstable. Right, so we now see that the lowest AIC corresponded to a P and Q value of 1 and 1. Right. So now, because it has the lowest AIC, we're going to pick those as our parameters, right? Because it has the lowest AIC. And if you remember also from the beginning, I said we are going to simulate an AIC process, and we're going to simulate an AMA process. And that AMA process also is the process 1 and 1, right? So now that we knew beforehand that our P and Q is 1 and 1, and now the model also told us also, like our process also told us that okay, it's also a 1 and 1. So we are going on with this, right? Now, in normal cases, you will not know, right? You will not know that this is your P and Q because the process, and we're trying to determine that, right? We are doing a test. And now for us to know if that P and Q is the right one, we're going to carry out two tests, right? The first one is the test of distribution, right? We're going to get the residuals. If you remember from machine learning, you know what a residual is, right? It's the difference between the true value and the predicted value, right? And so we're going to get the residual. I'm going to get a QQ plot, a quarter plot of that. And if the plot follows a straight line, we know that the residual is normally distributed. Normally distributed as in it is a random process, right? White noise. So we see that our model was able to like predict well, right? It was able to get the variations and everything the from the process itself. And we're also going to run I don't know how to pronounce this, a Junbox test, right? And this one is going to tell us is the autocorrelation too, right? Like how we did for the augmented decaffular test. All these tests have the long name. So we're going to also do the Junbox test, right? To test if the residuals are also not autocorrelated, right? We don't want a correlation because if there's a correlation, that means the model hasn't um, caught all the patterns in the data set, right? It doesn't cut up all the patterns because we want the model to get all the patterns and not be able to, it's not going to be able to model the noise, right? It's going to get all of the trends and everything, but it's not going to get the noise. So we want to make sure it doesn't get the noise because if it doesn't get the noise, that means it was able to predict the best it could, right? So I hope my explanation made sense, right? So that what we're going to do now, we're going to build a Cymax model with P and Q. We're going to rebuild it, right? With our data sets, we're going to fit, and we're going to get the residual. The residual is like the errors, right? And now we're plotting the QQ plots. And we see that it follows a straight line. It follows the normal distribution straight line, right? Right. And we can now say that the residuals are like white noise, like they're normally distributed, right? So we can also run another test with the model fit. We can also run also called the plot diagnostic test, right? So this plot diagnostic, sorry, not plot diagnostic test, the plot diagnostic method. It's going to help us plot all of the things we need. It's going to plot the residuals, right? We see that they're almost like they're stationary and they're just a random noise. It's also going to plot an histogram, a KDE plot. And we see that it looks like a normal process, right? This is how, if from statistics, you know what a normal process is, right? Normal distribution is. Also plots in the normal QQ plots, right? And we see that it also follows a straight line. And we also plots almost like the ADF test, right? We see that only the parameters with itself, that means the lag zero, right, is correlated, and that's normal. The rest are not correlated, right? So if you also run the junk box test, right, with the residuals, we also see that all of the values here are greater than 0.05, which means that the test, let me go back to what it says, right? The junk box test is the statistical test that determines the auto-calculation of the group of data is singular different from zero, right? In terms of if you apply the junk box test on model residuals, um, it's to test whether they are similar to white noise. So the null hypothesis states that data is independently distributed, meaning that there is no auto-correlation. So that's the null hypothesis. So if the p-value is less than 0.05, right, we can now reject that, right? But we see from here that the p-values are not greater than 0.05. So we stick with the null hypothesis and say that the residuals are normally distributed. I just hope that makes sense, right? So I can move on to the ARIMA model. If there are any questions, you can type it out in the chat. Okay, so let's go on to the ARIMA model. I just want us to be as fast as possible, to cover some things before the time. Okay, so the ARIMA model is just the AMA with the integrated in between, right? Autoregressive, integrated, moving average model. And so what's the difference? What's the fuss about? What's the fuss about, right? So it's the combination of the AR and MA processes, right? But in terms of the different series, right? So like I said, if you remember, in all the things we're doing, we're always going to do a difference, right? So that we make it stationary. And when we do that, we now end up with a difference time series, and we now have to do another transformation to get it to the normal time series, right? But now for the ARIMA, right? We now need to find out the D, right? The the order of integration, that's the D, right? So instead of doing all of that differencing manually, the model is going to do the differencing for us. That's just what it is. It's going to do differencing for us. So we now need to, what our job is to find the D, right? And most of the times, the the D is this is simply the minimum number of times a series must be difference to become stationary. That's self-explanatory as that's as self-explanatory as it can get, right? So most of the times we only difference a series once, right? And that means the D is going to be one. But sometimes also it's not always stationary, right? We still have a value very close to 0.05. So we can't really reject the null hypothesis. So we now have to difference it again. That means D is equals to 2. And then it most likely is going to be stationary. We don't need to difference a series more than twice in most cases, right? So we're going to just follow up with a simple use case, right? And I'm going to show you a Simon model and sorry, an RMA model. Most likely we'll try to get a SARMA model. And so we're going to run with a use case, right? So this is quarterly earnings per share for a particular company. Right? So this is the plot for the quarterly earnings per share, right? For over I think 1960 to 1980 and some months, right? Of a particular, I think Johnson's company. I've forgotten where the whole description data set is. So if we plot the data standardly, we see that sorry, it is not stationary. Yeah, it's not stationary. So we stick with the null hypothesis. Then we apply the differencing, right? And also, it's still not stationary. You see that we apply the difference and it's still not stationary. It still has a value very, very greater than 0.05, right? Now we have to difference it again. So we're differencing the difference series, and we have a second order difference, what's it called, series, time series. And now we run the AD Fuller test on it, and we see that we have a value less than 0.05 and a high negative value, not so high, but a high negative value. And so we can reject the null hypothesis and say that this is a stationary time series. So if you remember what we did for the AMA, right? The whole iterative process. We're going to do that for the RMA because we don't know the P, we don't know the Q, right? So we found out the D, right? We found out the D as 2, but we don't know the P, we don't know the Q. So we're going to do the iterative process all over again, right? And so what that means is that we're going to create a function. I've explained this function again. What we added is the D integer, and we're going to insert it into the Sari Max model, right? P, D, and Q, right? So now we're creating our list of P's, our list of Q's. We have our D as 2, and we create a list of P's and Q's, and including render. Okay. So we create our training sets, right? Remember, we have to get a train set. So what we're going to do, we are going to just remove the last 4 quarters. That means the last year, right? So this -4, since they're quarterly, is every 4 months. So we're going to remove the last 4 months, which is the last year. Train on the previous years, get the right P's and Q's, right? And we're going to stick with 3, P as 3 and Q as 3 because that was the lowest AIC score, right? So after that, we're not going to have to train again, right? We're going to train, get the diagnostics, plot out the histograms and the QQ plots. And yeah, we might see some issues here, right? But we'll stick with it because we haven't gotten to maybe the SARIMAs and stuff like that. So we're going to stick with it because it's still looking normal, right? If you look at this KDE plot or the KDE plot, it still looks normal, just like most likely skewed or yeah, most likely skewed, but yeah, it's still normal, right? And so if we plot the p-values, right? If we plot the p-values, we see some things. we see that some are very, very close to 0.05, but not really, right? But they're all greater than 0.05. So we can stick with the null hypothesis, right? That they are very close, but we can still stick with the null hypothesis that these are these are what's it called? These are not correlated residuals. The residuals are not correlated, right? Hope that makes sense. And so what we're going to do now is we're going to get our test set, naively create a naive solution, right? Naive solution of it. Just get the last values and just put that there, right? That's the naive solution. We're now going to predict, use our model to predict on the remaining values, right? And we're now going to insert that um, into the series. Now we're going to plot their difference. I'm sorry, I'm not plotting the difference. Remember, we didn't do the differencing again. The model that did the differencing for us. So we get that, and we're now going to plot um, the naive with the ARIMA model, and we see that the naive was not really that good compared to the ARIMA model that almost got close or actually close with the actual prediction. So the actual values, right? So if we now get we have to use the metric, right? We can't just use plots. We have to get metrics to evaluate with numbers. How good is this model, right? So we're going to use the the mean absolute precision. No, not mean absolute precision. Yeah, mean absolute precision. No. Mean absolute percentage error. Right? So, and if we do that, we get the MIP as 11 for the seasonal and 1 for the ARIMA. And we plot that, we see how far apart they are. So we see that the ARIMA model is really good for this process, right? So let's go to the SARIMA. Most likely we'll stop here for today. If there are any questions, please, you can ask now. Okay. I would say the silence means that everybody is understanding what I'm saying. So now this is where we'll stop for today. So the SARIMA model, right? We have done the AMA, we have done the ARIMA, now we're in SARIMA. And I think the name should like bring some hints, right? All this while we have been ignoring the seasonalities, right? Seasonalities as in something like this. We see that in some months of a year, there are peaks and there are troughs, right? There are troughs and there are peaks. So that means there's seasonality, right? So maybe by July, August, I've forgotten, by July, August, we see that there are some dips. Sorry, by July, August, there are some peaks, and maybe in the beginning of the year, there are some troughs, right? So that's seasonality, right? So that's where the comes in, right? So there are now like other values we need to account for. The normal PDQ, right? And also capital P, T, and Q. When we see that there are some more complexities with the SARIMA model. And so we'll try to explain all of that as we go on. All right, so let's see. We have, sorry, okay. So for the SARIMA model, what we need to determine is the M, right? What is M? M is the frequency or number of observations, like the seasonal. Okay, if you take data every month, right? Your M is 12. If you take data every day, your M is 365 or 366. If you take your data every week, your M is 52 because there are 52 weeks in a year. I hope you are getting a pattern. If you get your data every second, you multiply 60 by 60 by 24 by whatever to get how many seconds it is in a year. So that's your M. So what the important thing is that, or what's important is that what this accounts for is that, that if you look at this part of the year is most likely determined by this part of the year, right? It's most likely related to this part of the year, right? And which is so yeah, like saying that August of the last year is very, very important to August of is dependent or is very, very dependent on August of this year, right? So that's why we're using that M to subtract, right? So instead of just looking at a day or 2 days or 3 days, like in moving average, so in the autoregressive process, we're now subtracting the number, the M, to get the actual months, right? That is important to this particular day, right? So that's just what it is. That's what the sign is. I hope like we understand. So what we're doing is that we're getting a data set of people that took flights between some year 1949 to 1961 for a particular airport, right? And we know like normally people tend to travel by air in some particular months and some other months, right? Because of holidays and whatnot, right? So we get the data, we plot it, like so. You can always look for seasonal patterns, right? By just visually looking at it, right? You can do that, right? But in some cases, you might not be able to see the periodic patterns, maybe because you have a large amount of data, right? You will not be able to see them visually by just plotting, right? So you you have to do something called a time series decomposition, right? And to do that, we just need to import a module from stats model called STL, right? So it's going to help us do some seasonal decompositions for us, right? And when we now run, like you put in data sets and the period in which data was taken, right? Like I said, this one is 12, right? Every is every it was a monthly data, month one, month two, month three, month four, January, February, March, April. So the period is 12, and we fit with that particular module, and we get something. We get the observed data. This looks like data we have a trend. We see that the trend is going upwards, like it's an upward trend with time. We now see seasonalities, right? We see that there are seasonalities in data. So if there was no seasonality, we most likely see a straight line. I mean that there's no seasonality. I mean that you just need to stick with normal RMR, right? But if you see a seasonal pattern, like seasonal trend, we know that we need to use Sarima model, right? Or Sarimax and whatnot, or Prophets, right? So this is not the residual. We always see that the residual is always random, right? Like a random stationary process, right? So first thing we do, we need to determine what is our D, right? And we most likely stick with D as 2, right? D is most likely 2 because when we run
Hello, has the class ended?